Okay, I think we last left off at user preemption. Before I do that, let's just make sure that my kernel is back to where it was before I broke it. I think it was building, and then I just basically did the make install and update grub again. So hopefully, hopefully we're able to boot. It still has some of our old logging though. Hmm, come on, yeah, cool. So it's fixed. Great. Okay. All right. User preemption. User preemption occurs when the kernel is about to return to user space. Need reschedule is set, and therefore the scheduler is invoked. So remember, need reschedule is basically forcing the scheduler to pick a new process to run. If the kernel is returning to user space, it knows it is in a safe quiescent state. In other words, if it is safe to continue executing the current task, it is also safe to pick a new task to execute. Consequently, whenever the kernel is preparing to return to user space, either on return from an interrupt or after a system call, the value of need reschedule is checked. So whenever you're in kernel space and then you need to return back to user space, you need to check this need rescheduled value. So if it is set, the scheduler is invoked to select a new, basically more appropriate process to execute. Both the return paths for return from interrupt and return from system calls are architecture dependent and typically implemented in assembly in entry.s, which aside from kernel entry code also contains kernel exit code, kernel.s. So that's assembly. I think there's like a bunch of entry.s's that are very specific to architecture. So if you have x86, I think there's a specific folder where that's included. So let's see what we get here if we were to look for it. Still searching. So we do have entry.s for alpha. And then we also have entry.s for whatever HA300. And then we'll have entry.s for score, Sun Plus Core Technology, S390, System 390, ARC V10. I'm guessing we're going to have an x86 somewhere down here. If I did x86, would that do anything? No, that doesn't work like this. How about Arch x86? Oh, okay. Entry. What's the format of this? Kernel slash entry.s. So if I did x86 slash kernel slash entry.s, there's no one? There's no entry.s here? Okay. Oh, this is correct. Let's see if I can have a file called entry.s. This is more like it. Okay. So I'm guessing we don't have one. Here we go. Entry 32 and entry 64. So let's look at the simpler one and do entry 32. So entry.s contains the system call and fault low level handling routines. Okay. So this is it. This is written by Linus Torvalds in 1991 to 1992. Okay. So it is all literally x86 assembly. So no idea what it says. Can move on. In short, user preemption can occur when returning to user space from a system call or when returning to user space from an interrupt handler. Kernel preemption. The Linux kernel, unlike most other Unix variants, so Linux kernel is different here in this kernel preemption, and many other operating systems, is a fully preemptive kernel. Okay, what does that mean? Well, in non-preemptive kernels, kernel code runs until completion. So when the kernel gets to run, the kernel will actually just run until it's done with its job. That is, the scheduler cannot reschedule a task while it is in the kernel. Okay, kernel code is scheduled cooperatively, not preemptively. Kernel code runs until it finishes. It returns to user space or explicitly blocks. Okay, so that's not Linux right now. Now in the 2.6 kernel, however, the Linux kernel became preemptive. It is now possible to preempt a task at any point, so as long as the kernel is in a state in which it is safe to reschedule. So when is it safe to reschedule? The kernel can preempt a task running in the kernel, so as long as it does not hold a lock. That is, locks are used as markers of regions of non-preemptibility. Because the kernel is SMP safe, if a lock is not held, the current code is reentrant and capable of being preempted. Okay, let's try to understand what that means. So the kernel is SMP safe, meaning that it's multi-threaded. If a lock is not held, the current code is reentrant and capable of being preempted. So what does reentrant mean here? So in computer, oh, what the heck? Okay. Reentrant. Okay. Reentrant means what? Computer science. Reentrancy. Reentrancy is a computer programming concept where a function or subroutine can be interrupted and then resumed before it finishes executing. Okay, reentrant, that means you are basically you're able to be interrupted, okay, or context switched away in the middle of something, and then later come back to it. So your normal context switch. So the whole sentence says, if a lock is not held, okay, the current code is assumed to be reentrant and capable of being preempted. Okay, that means the assumption is that at any point, if you do not have a lock, if you don't claim a lock on something, right? At any place in execution, a process or a task, in this case, can just be switched out and then scheduled later, and another task will run in its place. And that's a problem. You're not holding on to lock. And also, you have to always consider that at any point in time, your task won't be able to execute everything in one shot. At any point in time, your scheduler can just decide that it's time that you actually get back to the queue, to the run queue, and have somebody else execute. Okay, and if that person is executing on something, like maybe it's another thread that on memory that you might need, right, then that could potentially cause a lot of issues with your data. So the first change in supporting kernel preemption was the addition of a preemption counter, preempt_count, to each process's thread info. This counter begins at 0 and increments once for each lock that is acquired and decrements once for each lock that is released. When the counter is 0, the kernel is preemptible. Upon return from interrupt, if returning to kernel space, the kernel checks the values of need reschedule and preempt count. If need reschedule is set and preempt count is 0, then a more important task is runnable and it is safe to preempt. Okay, so need reschedule set, that means, okay, go ahead and pick another task, and the preempt count is 0. And what does preempt count mean? Preempt count is incrementing once for each lock that is acquired and decrements once for each lock that is released. Meaning, if preempt count is non-zero, there's a lock, right? So if need reschedule is set and there are no locks, then that means a task, you can run another task in its place. Okay, so now if preempt count is a non-zero, it means that there is a lock being held. And if need schedule is set at that same time, then it is not safe to preempt. Okay? It is only safe to preempt if need schedule is set and preempt count is 0. So thus, the scheduler is invoked if preempt count is non-zero, a lock is held, and it is unsafe to reschedule. Yeah, there we go. Should have just read, continue reading. In that case, the interrupt returns as usual to the currently executing task. Meaning that if I was a task that just woke up or whatever, right, then I have to continue executing. So when all the locks that the current task is holding are released, preempt count returns to 0. At that time, the unlock code checks whether need reschedule is set. If so, the scheduler is invoked. So that's interesting. So let's say I was holding onto a lock, right? So preempt count was non-zero. Okay, the second I release the lock, and if need reschedule is set, what is telling the scheduler to do is to go find a more appropriate task to run next right away. Okay, so enabling and disabling kernel preemption is sometimes required in kernel code and is discussed in chapter 9. Kernel preemption can also occur explicitly when a task in the kernel blocks or explicitly calls schedule. This form of kernel preemption has always been supported because no additional logic is required to ensure that the kernel is in a safe state that is safe to preempt. It is assumed that the code that explicitly calls schedule knows it is safe to reschedule. So kernel preemption can occur, okay, when an interrupt handler exits before returning to kernel space, when kernel code becomes preemptible again, and if a task in the kernel explicitly calls schedule, and if a task in the kernel blocks, which results calls schedule. Okay, so you preempt at the kernel level when any of these things happen. Okay. Linux. Okay, so now let's do real-time scheduling policies. Okay, so Linux provides two real-time scheduling policies: Schedule FIFO and Schedule RR. So I'm guessing this is like first in, first out, and then round robin. The normal, not real-time scheduling policy is Schedule normal. Okay. The normal, not real-time scheduling policy is Schedule normal. Okay, sure. Via the scheduling class framework. These real-time policies are managed not by the completely fair scheduler, so CFS, but by a special real-time scheduler defined in schedule.rt.c. So a different scheduler, not the CFS one. So this is a different one now. The rest of this section discusses the real-time scheduling policies and algorithm. So Schedule FIFO implements a simple first in, first out scheduling algorithm without time slices. Okay, no time slices again. Simple. A runnable Schedule FIFO task is always scheduled over any Schedule normal tasks. Okay, when a Schedule FIFO task becomes runnable, it continues to run until it blocks or explicitly yields the processor. It has no time slice and can run indefinitely. Whoa, okay, sure. Only a higher priority Schedule FIFO or Schedule RR task can preempt a Schedule FIFO task. 2 or more scheduled FIFO tasks at the same priority run round robin, but again only yielding the processor when they explicitly choose to do so. So it's kind of like a cooperative scheduling, where we had to like trust the process to either like give up its CPU time. If scheduled FIFO task is runnable, all tasks at a lower priority cannot run until it becomes unrunnable. Schedule RR is identical to schedule FIFO, except that each process can only run until it exhausts a predetermined time slice. That is, schedule RR is schedule FIFO with time slices. It is a real-time round-robin scheduling algorithm. When a schedule RR task exhausts its time slice, any other real-time processes at its priority are scheduled round-robin. The time slice is used to allow only rescheduling of the same priority processes. As with schedule FIFO, a higher priority process always immediately preempts a lower priority one, and a lower priority process can never preempt a schedule RR task, okay? Even if its time slice is exhausted. Sure. Okay. Both real-time scheduling policies implement static priorities. The kernel does not calculate dynamic priority values for real-time tasks. This ensures that a real-time process at a given priority always preempts a process at a lower priority. The real-time scheduling policies in Linux provide a soft real-time behavior. Soft real-time refers to the notion that the kernel tries to schedule applications within timing deadlines, but the kernel does not promise to always achieve these goals. Conversely, hard real-time systems are guaranteed to meet any scheduling requirements within certain limits. So Linux real-time scheduling isn't like really hardcore real-time scheduling. Linux makes no guarantees on the capability to schedule real-time tasks, despite not having a design that guarantees hard real-time behavior. I think that's changed with like recent kernel changes in the 6.11 or something like that. The real-time scheduling performance in Linux is quite good. The 2.6 Linux kernel is capable of meeting stringent timing requirements. That's reassuring. Oops. Okay. Okay. So real-time priorities range inclusively from 0 to max RT prio minus 1. So 0 to max RT prio, but 1 less than that. By default, max RT prio is 100. Therefore, the default real-time priority range is 0 to 99. This priority space is shared with the nice values of scheduled normal tasks. They use the space from max RT prio to max RT prio plus 40. By default, this means that the negative 20 to 19 nice range maps directly onto the priority space from 100 to 139. What? By default, max RT prio is 100, okay? Therefore, the default real-time priority range is 0 to 99. Okay, makes sense so far? This priority space is shared with the nice values of scheduled normal classes, scheduled normal tasks. So the normal scheduler, okay, with the nice values, they use the space from max RT prio to max RT prio plus 40. Oh yeah, because there's 40 nice values. Okay, got it. So by default, this means the negative 19 to the 19, negative 20 to 19 nice range maps directly onto the priority space from 100 to 139. Okay. Uh-oh. The hell? Okay. All right. So scheduler related system calls. Linux provides a family of system calls for the management of scheduler parameters. These system calls allow manipulation of process priority, scheduling policy, and processor affinity, as well as provide an explicit mechanism to yield the processor to other tasks. Interesting. Okay. Various books and your friendly system man pages provide reference to these system calls, which are implemented in the C library without much wrapper. They just invoke the system call, okay? Table 4.2 lists the system calls and provides a brief descriptions. How system calls are implemented in the kernel is discussed in chapter 5, system calls. Interesting. Okay, let's come back. Actually, let's see what it does. So sets a process's nice value. That's interesting. Okay. Set scheduler sets a scheduling policy. Set param sets process real time. Get priority max. Get priority min. Set affinity. Interesting. Temporarily yields a processor. Gets a process's time slice value. So this is for the real time stuff. But this is interesting. Sets a process's nice value. Okay. Scheduling policy and priority related system calls. Okay, so I think they're going to go to discuss all the system calls here. So let's do it. Okay, so the schedule set scheduler and schedule get scheduler system calls sets and gets a given process's scheduling policy and real-time priority respectively. Their implementation, like most system calls, involves a lot of argument checking, setup, and cleanup. The important work, however, is merely to read or write the policy and RT priority values in the process's task struct. The schedule set param and schedule get param system calls set and get a process's real-time priority. These calls merely encode RT priority in a special schedule param structure. This calls schedule get priority max and schedule get priority min. Okay. Return the maximum and minimum priorities respectively for a given scheduling policy. The maximum priority for real-time policies is max user RT prio -1. The minimum is 1. For normal tasks, the nice function increments the given process's static priority by the given amount. Only root can provide a negative value, thereby lowering the nice value and increasing the priority. The nice function calls the kernel's set user nice function, which sets the static prio and prio values in the task struct as appropriate. Okay, let's see that set user nice function. So if we did this, actually, set user nice. Is there such a function called set user nice? Oh, there we did. Well, you see that's always calling it here, but where is it defined? So I did it right here. No. Is it here? Interesting. So, if the nice value of the task is equal to the current nice value, or nice is out of range, then return. Okay. Task nice. What does that do? I'm guessing that gets the nice value. Prio to nice. Okay. So set user nice. Okay. So this gets the nice value. Then this will actually then set the real priority. This is RT. So if this is a real-time task, it's going to figure out the real-time priority and then go to unlock. Otherwise, static priority is computed from, again, the nice value, the current nice value. And the current nice value is being passed here as a long. Okay. And P is indeed a task struct. Sure. Okay. Interesting. It was reschedule the task. So if the task increases its priority or is running and lowered its priority, then reschedule CPU. Sure. If it's on the run queue, we have to in-queue the task again. Then reschedule it. So what's with this old priority? Old priority is P prio delta. Oh, the change. Okay, it needs that. And then effective priority. Sure. I wonder if we can like detect whether or not there's a specific process that's running. We can rewrite the nice value to something else. I kind of just want to do that for fun. All right, so like let's say for example, like we had, let me just look at. So let's do PS. I think PSE will tell us what we have. No. PSU. That's just what I have as myself. How about PS EX? Okay, that's like the full path. The command, the com. Okay. So I could really mess this up if I did this. Okay, let's actually pick a process. You know what? Let's pick I guess the word processor, open office. What is this? Open office. So if I did ps aux grep open. Okay, so open office, s office, bin, writer. Oh, that looks complicated. Open. Okay, no, I don't want to do open office. Let's do something easier. Let's just do graphics program. F spot. Let's just do gedit. Okay, so gedit. So if I did this, gedit. Okay, so gedit is going to be the com name. And then how do I look at the priority again? I forgot how to look at the priority. PS display priority. L. Okay, so L. So what is gedit? PS dash L. Wait, LX. Okay, so that's what I want. Okay, and then grep gedit. Okay, so gedit right now is what? Bad PS syntax. Why? Whatever. 0, 0. So 0 right now. So what happens if I like do something crazy and just like, oh, priority is 20. So what's NI? Negative 11. What happens if I just set it to like negative 19? I wonder what would happen by default. So if I did something like this, it's super useless. So I'm just gonna do this. If p com, right? How do I do string equals? So how do I compare string? Ooh, let's bring up. Okay. So how do I compare strings in Linux 2.6 kernel? In Linux 2.6 kernel, you compare two strings using several methods. Stir and eq. Okay. So Linux string.h. So we need the length. Strcomp. Okay, strcomp. Okay, let's do strcomp. So there is the same sort of thing. So if I did, so I'm at here. I should probably add a comment. Or actually, Yeah, let's do this. Stir cmp com with gedit. Okay, so we have gedit, and that's like equal. Okay, I'm gonna do print k kern info average dev setting nice priority of okay to -19. Yeah, let's do that. Okay, so now this is one with pcom. Okay, so we want to just do something like this. All right, now nice will be -19. Okay, so that's -20. Sorry, it goes the other way around. So this is the highest priority, just for fun. I know we can actually do this with just normal OS like system call, but I just want to see what happens. And then we can import the Linux string h. Okay, so we did that up here. Where are all the includes at? Okay, so Linux string h, is it already imported? No, so I could do include Linux string.h. Okay, so now if I were to search average dev again, basically I'm just going to check to see if the process's name is gedit, and then if so, I'm just going to set the nice to -20 and see what happens. I don't know, this is completely useless, but just fun stuff. Okay, so if I just did make j 48, for example. Okay, so let's just let that cook a little bit, and then we'll keep going. Okay, so processor affinity system calls. The Linux scheduler enforces hard processor affinity. That is, although it tries to provide soft or natural affinity by attempting to keep processes on the same processor, the scheduler also enables a user to say this task must remain on this subset of the available processors no matter what. So this hard affinity is stored as a bit mask in the task structs as CPUs allowed. Okay, the bit mask contains 1 bit per possible processor on the system. By default, all bits are set, and therefore a process is potentially runnable on any processor. Okay, the user, however, via schedule set affinity can provide a different bit mask of any combination of 1 or more bits. Likewise, the call schedule get affinity returns the current CPU's allowed bit mask. Okay. The kernel enforces hard affinity in a simple manner. First, when a process is initially created, it inherits its parent's affinity mask. Because the parent is running on an allowed processor, the child thus runs on an allowed processor. Second, when a processor's affinity is changed, the kernel uses the migration threads to push the task onto a legal processor. Okay. Finally, the load balancer pulls tasks to an only allowed processor. Therefore, a process only ever runs on the processor whose bit is set in the CPU's allow field of the process descriptor. Sure, but by default, what? By default, what? All bits are set, so a process is able to run on all processors. Okay, so that's done. I don't even know how to test. I think we just need to like change the nice value somewhere, and then it'll force the gedit to always run at a specific nice value. So I think it says change priority here, for example. Okay, so we can just change that, and we'll see that it's always going to lock down to -20, for example. So if I just did, for example, gedit here, and I said to change priority, for example, there, since it's negative, I have to, yeah. So we should always see negative 20 or whatever once we install a kernel. So you make install. Okay, then sudo update grub. And sudo reboot. Okay. All right. This is just for fun. See if we can actually do more things, you know. Let's go slow, basic things. Okay. Let's see, what have we broke? So far, so good. Alrighty. A program is still running. Cancel? Did I log out or something? What did I do? Wait, what? Did I broke something? I broke something. I broke something. I broke something. Uh-oh. Uh-oh. That was the wrong one. Crap. That was my lock screen, so I'm good. We'll come back to that later. let's just restart. Let's see here. I probably locked up. Negative 19 is probably not good. Okay, but anyway. Yielding processor time. Linux provides a scheduled yield system call as a mechanism for a process to explicitly yield the processor to other waiting processes. It works by removing the process from the active array where it currently is because it is running and inserting it into the expired array. This has the effect of not only preempting the process but putting it at the end of the priority list, but also putting it on the expired list, guaranteeing that it will not run for a while. Because real-time tasks never expire, they are a special case. Therefore, they are merely moved to the end of their priority list and not inserted into the expired array. In earlier versions of Linux, the semantics of scheduled yield call were quite different. At best, the task was moved only to the end of the priority list. The yielding was often not for a long time. Nowadays, applications and even kernel code should be certain they truly want to give up the processor before calling scheduled yield. Kernel code, as a convenience, can also call yield, which ensures that the task state is task running and then called scheduled yield. User space applications use the scheduled yield system call. So scheduled yield is the system call. Cool. Okay, if I log in, am I broken? Oh, I probably just fat fingered something. Okay. So if I did the message, okay, so far so good. I guess this is all from last time. And then if I did, let's see here, G edit. Okay, let's see what we get. Okay, nothing here. Okay. Now, if we did administration, system monitor, so now gedit should be here. But if I change the priority, just even like change it to 8. For example, what happens? Oh, look at there. It's negative 20. It doesn't even check for permissions too, because I bypassed all that. So it's like you had to be root. Well, forget it. You can. So basically, even in here, I'm guessing there was like some sort of check here, but I inadvertently bypassed all that, I guess. But yeah, it's negative 20 now. I don't even know like what the significance of it is. Let's see. If I did, do we have top here? Yeah. So priority, we have real-time ones. Do we get gedit? Yeah, gedit negative 20 is a nice value. These are not real-time though. Okay, so I mean, we forcefully, I mean, I think if we were to like, let's say, try to change priority as something else, right? We would need to. Oh, I probably. Oh, I. Oh wait, no, I had to go negative in order to have it complain to me that I don't have permissions. Okay, yeah. So this one, nice, right? Nice. I need to be sudo, right? But with this one, I think I'm free to do whatever I want because I hard coded it to always be negative 20. So interesting. Anyway, the process scheduler is an important part of any kernel because running processes is, for most of us at least, the point of using the computer in the first place. Juggling the demands of process scheduling is non-trivial. However, a large number of runnable processes, scalability concerns, trade-offs between latency and throughput, and the demands of various workloads make a one-size-fits-all algorithm hard to achieve. The Linux kernel's new CFS process scheduler, however, comes close to appeasing all parties and providing an optimal solution for most use cases with good scalability through a novel and interesting approach. The previous chapter covered process management. This chapter ruminated on the theory behind process scheduling and specific implementation, algorithms, and interfaces used by the current Linux kernel. The next chapter covers the primary interface that the kernel provides to running processes. System calls. Okay, have a little time just to read a little bit of it. Okay, system calls. In any modern operating system, the kernel provides a set of interfaces by which processes running in user space can interact with the system. These interfaces give applications controlled access to hardware, a mechanism with which to create new processes and communicate with existing ones, and the capability to request other operating system resources. The interfaces act as the messengers between applications and the kernel, with the applications assuming various requests and the kernel fulfilling them or returning an error. The existence of these interfaces and the fact that the applications are not free to directly do whatever they want is key to providing a stable system. So I guess before I head off, basically what a system call is, I'll just do green, is that it's providing basically an abstraction above the kernel and user space. Right, so in this case it could be like gedit, and this is like Linux, and then this is just the hardware. Whenever, like, let's say gedit wants like save a file, open a file, just basically make access to kernel things, it has to go through here by calling a system call. Then the system call goes to whatever is implemented by the kernel, and then it does stuff. So this is, think of this as like the kernel API. It's not exactly accurate, but that's how a user space program like gedit interfaces with the kernel just through these system calls. So system calls, you could write to a file. You can even like change the process priority like we did right here. You can do many things. So anyway, good stuff. We've made through 5 chapters. It's a little slow, but it's because it's hard stuff. Okay, thanks.